Okay, so last time we were talking about carboxylic acids, and now we're going to talk about their derivatives. I warn you, this particular topic is kind of heavy, and this particular lesson is kind of heavy. So let's make sure we start with naming all of these guys. So first you have an acyl chloride, and what we do is we replace the E and end with oil chloride. So this would be a butanoyl chloride because you've got 1, 2, 3, 4 carbons there. So instead of it being butanoic acid, we've got butanoyl chloride. Here we've got 1, 2, 3, 4, 5. That's 3-methyl pentanoyl chloride. And finally we've got 2 isopropyl hexanoyl bromide. Next comes acid anhydrides, and the reason why we call these anhydrides and acid anhydrides specifically is that you basically take 2 acids and you dehydrate them. In other words, anhydride. So it takes out the water, and instead you end up with a single oxygen in here. So there's hydrogen from 2 of these plus an oxygen. That's where you get the H2O from. And so these are things that we typically use in the lab quite a bit, especially acetic anhydride, so we're actually using that in the lab as well right now. And it's really easy when the 2 sides agree with each other, they're symmetrical. We just call this propanoic anhydride, so instead of it being propanoic acid, it has been dehydrated, so we call that anhydride. This would be acetic anhydride. If they're asymmetrical, in other words, you have 2 different acids that came together to make this guy, then we just list them alphabetically. So this would be acetic acid if it were over here, and this would be propanoic acid over here. So we list it as acetic propanoic anhydride. We've got 1, 2, 3, 4 here, and 1, 2, 3, 4, 5 here. So this becomes butanoic pentanoic anhydride. Okay, next comes esters. And esters, I actually see these written incorrectly a lot. The carbon that's in the carbonyl, that's your parent chain. Everything that's coming off of this guy is your substituent, off of the other oxygen. So we call this 1, 2, 3, that's propyl, and then we say that this is ethane, take off the E, O8. So propyl ethanoate. And this is very similar to what we named carboxylates, right? So again, here's your substituent. This is cyclopentyl propanoate. Here we've got a benzyl group, and that's 1, 2, 3, 4 butanoate. Okay. And finally, amides. Amides are very important for biochemistry. So definitely need to know how to look at amides, and we'll talk about that as the semester goes on too. But basically what we do is we replace the E of the parent chain, and we replace it with the term amide. And you can have, well, here, let me do this first. This would be 1, 2, 3, so that's propanamide. We've got 1, 2, 3, 4, 5, 6. That's hexanamide, but we have a methyl group right here, so that becomes 2-methyl hexanamide. Again, you're going to start numbering right here. That's 1, 2, 3, 4, 5, 6. Now, if you have something that's coming off of the nitrogen, its location is N. And we put that in italics, but it is a capital N. So I've got substituents as an ethyl group here. I've got a methyl group here and here. And this is a 1, 2, 3, 4 carbon chain. So we're going to put it in alphabetical order just like we would if it was any other number. This becomes N-ethyl, 2N-dimethyl. 2 numbers come before letters in the alphabet, and that's the reason why it's 2N, not N2. Butanamide. Okay. So next we need to look at some of these with reactivity. There's a general mechanism that we're going to see with these types of reactions, and I'll go over that before I show you why things happen as they do. So a nucleophile is naturally attracted to that carbon. Why? Because it's got a partial positive charge to it, right? And so when this nucleophile comes and attacks, those electrons go up. As the electrons come back down, basically you've got to decide which of these two is most stable on its own. The one that's the most stable on its own is going to come off. And if that happens to be what was on there before, bam, he just came off. And so you get a new nucleophile right there. So that means that this guy is pretty reactive because chlorine, as it comes off by itself right here, is pretty stable. However, if you were to look at NH2 minus, which is what that would be there, that's very unstable, which means that this guy, he's not very reactive. That's kind of a good thing considering how your molecules go together, okay? So if you want to consider it that this is the most reactive and this is the least reactive, feel free to do that. If you want to consider it that this guy's most stable on his own and that's why he's most reactive, and this guy's the least stable on his own and that's why he's least reactive, that's also true. So let's start looking at some reactions with acyl chlorides specifically. We can take this carboxylic acid with SOCl2 and still replace this OH right here with a Cl. So that's how we make them. So you make your carboxylic acid first. You can see some great synthesis there, right? Then we do this, and then we can do other stuff. That's exactly how we do those. Excuse me. If you have water and pyridine, so pyridine is just being used as a base here to neutralize your acid that you're making, you can make a carboxylic acid. So here's the mechanism. This guy comes in here, electrons pop up, he comes down, kicks this guy out because he's willing to be on his own, and then the base, it could be the pyridine, it could be another water molecule, whatever that may be, will come and rip off that hydrogen, and there you go. You can do the same type of thing with alcohols. So that's the only difference, is that you end up with an ester instead of a carboxylic acid. Okay. Very similarly also, we can use any type of amine or NH3 to give you an amide. So essentially what this is showing is that this guy reacts with him, or an OH right there. That's exactly what we anticipate seeing. Acyl chlorides can also be reduced. We use lithium aluminum hydride with these to get them down to a primary alcohol. Now this is something that's similar to a couple other things that we've seen also. The hydrogen, sorry, this is like the worst rendition of lithium aluminum hydride I think I've ever drawn. So that's my mistake. But these electrons come over here and attack up, and that sends that up. Now, you've only got one thing to leave here, right? So when these electrons come back down, that leaves. Now we've got an aldehyde. Well, he loves aldehydes. So he brings over his electrons go up again, and then he finds some type of proton source to give you that alcohol. If you instead wanted this reaction to stop at the aldehyde stage, you can use a less reactive version of lithium aluminum hydride, which is got these T-butyl groups and oxygens in here. And what that essentially does is it weakens the strength of that hydride. Plus it only gives you one hydrogen on each of the aluminum, so it can be a little bit more succinct with measurement too. So we have that acyl chloride, and we end up with the aldehyde just right there. Acyl chlorides are like esters in that they react twice with Grignard reagents. So you would start off with an acyl chloride and you'd end up with two R groups here, whatever this R group is right there. So here's the mechanism for that. So electrons come in here, and this pops up, and then they come down and that leaves, because obviously CH3 is not going anywhere. Another equivalent of Grignard would come in, move those electrons up, and then that would find some proton source when you acidify it or put water in there, and you get that alcohol. And finally, these still do react with Gilman reagents or Cooley, and then you would end up with a ketone that way. Thank you very much.